you for attending this talk. This presentation is about emerging technologies for sensing and processing for robotic vision, particularly a novel paradigm where sensing and processing are performed on the same chip on the focal plane. Photography cameras have been around for almost 200 years. The first commercial camera was made available in 1839. These cameras were meant to produce images for us, humans, so when our eyes look at them, we could make sense of the world. For robotic applications, we are using a camera technology that has been designed for a different purpose. Here's a question. Are the photography cameras the right choice for the robotic vision? We will see an alternative solution here, known as focal plane sensor processor arrays or FPSPs, which have major advantages over photography cameras in robotic applications. In conventional or standard sensing and processing architecture, we typically see a sensor shown on the left and the processor shown on the right. The sensor is composed of a grid of light-sensitive elements that capture the photons and convert them to electric charges stored as analog values. The analog values are then digitized with an A to D. The digital image is then sent to the processor. These images capture a lot of data, but the main drawbacks of this architecture are the motion blur at high speeds, latency caused by A to D, and the need for high bandwidth to transmit all those data. Event cameras, also known as silicon retina or dynamic vision sensors (DVS), were presented to address the drawbacks of the standard cameras. Event cameras capture the light photons like the standard cameras, and then using some fast and simple electronic comparators, only changes in intensities are sent to a host processor. Each event includes the UV coordinates of the pixel, the polarity of the change in intensity, and the timestamp of the event. Events are asynchronous, which means the pixels work independently. Event cameras do not suffer from motion blur, but the processor should be powerful enough to process all the events in highly dynamic scenes that produce a lot of events. In this video, you will see the standard and conventional systems. When the disk is spinning, the standard camera captures frames and the event camera captures the changes. When the disk stops, there are no events, but the standard camera captures and sends the same frames over and over. When the disk spins too fast, the standard camera experiences motion blur, but the event camera can capture all events. In the standard and event cameras, the sensor and the processor are two different entities physically separated from each other. In the emerging paradigm of co-located sensing and processing, these two entities are co-located on the same chip. This is known as the focal plane sensor processor arrays or FPSPs, where there is some processing capability right before the electric charges representing the image are digitized. The processing is done in analog and only the results are digitized, so there is less load on analog to digital converter. Also, processing in analog is much faster. Therefore, the system has a very high effective frame rate. You can program the device to output events just like the event cameras or output any other abstract information. Inside an FPSP, every pixel has a light-sensitive element with a processing element, which can perform the computation on analog signals. Pixels can communicate with each other. Each pixel has access to the values of pixels on its north, east, west, and south, also known as news. Pixels have access to the values of further pixels via this communication method. SCAMP5 is an FPSP designed and developed at the University of Manchester, and I will show you some experiments done with SCAMP5. SCAMP5 has 256 by 256 pixels. Each pixel has 7 analog registers and 14 bits. There is no central memory on the chip. There are 170 transistors per processor, and computation on SCAMP5 is performed in analog using these transistors. There is no digital capabilities such as flip-flops, and all computation is done in an analog fashion. On the FPSP, the processing is done in SIMD or Single Instruction Multiple Data Paradigm. All pixels implement the same instruction on their local data. The supported instruction set is very simple. You can add or subtract two images held in registers. You can also scale down an image by a factor of 2 for multiple times. You can shift the image in X and Y directions. There is no multiplication though. Now we will look at the first application of SCAM5 in computer vision. We will see how we can perform kernel convolution on the focal plane using these simple instructions. For the shown matrix M and kernel K, the classic definition of convolution is shown by sigma. The convolution described in figure A is performed on FPSP by shifting M in two directions and adding the results. The shift and addition operations are derived according to the kernel. In figure C, an abstract graphical representation of what you saw in figure B is shown. In step 0, a random pixel is shown which holds its own value by a multiplication factor of 1. In step 4, after shift and addition operations, the same pixel holds factors of adjacent pixels as specified by the kernel. Let's look at the details. In step 0, assume the image is in register A. In the next step, step 1, the image is shifted north, which is downwards. The shifted image is stored in register B. In step 2, the shifted image and the original image are added up and the results is stored in register B. In step 3, the original image is also shifted to west, which points to the right. Finally, in step 4, the result of step 2 and step 3 are summed up. The code for this convolution is composed of 4 instructions. We can easily extend this approach to perform more complicated kernel convolutions. It is possible to perform convolution with any kernel. You can easily implement the convolution on FPSP for a kernel with integer values as shown on the top row, or for any kernel with the elements of powers of 2 as shown in the middle row. Also, it's possible to do convolutions for kernels with any values by approximating the values to the nearest power of 2 as shown in the last row. In this slide, you will see the performance of convolution on multiple different devices such as GPUs, CPUs, and FPSP. Different filter kernels such as Gaussian, Box, and Sobel are used here. Figure A shows the execution times of a single application of various filter kernels on different hardware components. On the x-axis, you see different kernels, and on the y-axis, you see the execution time. The results are shown for 4 CPUs, 3 GPUs, and a SCAM5 FPSP. The parallel nature of the SCAM5 FPSP allows it to perform all the tested filter kernels in a fraction of time needed by the other devices. The table reports the energy the devices spend per single filter application. The Titan X GPU has the highest power consumption for all filters. SCAM5 FPSP has not only the smallest computation time per filter, but also the lowest power consumption. The energy spent per frame is much smaller than for any other device. Now that we can do the kernel convolution on FPSP, we can also do CNNs on FPSP. A simple network for the handwritten digit recognition challenge is shown on the left. We have chosen a simple network because the camera has limited computational resources. The network is composed of 3 kernels, a pooling layer, and a fully connected layer. This network has an accuracy of 97.1% on CPU and GPU, where all the network runs on the digital processor. On the SCAM5 FPSP, we can perform the convolutions and pooling on the chip, and only the activation results are sent to a digital processor to perform the last layer computation. The accuracy of the FPSP is very similar to the accuracy of the conventional digital system. The difference in accuracy is due to the noisy computation of the analog values on FPSPs. But the interesting part is in the next slide. Here on the left, you see the runtime speed for the digit recognition challenge. On the x-axis, CPU, GPU, VPU, and FPSPs are shown. VPU is the vision processing unit, which is a highly optimized hardware to run neural networks. It's been designed by Intel Movidius. On the y-axis, per-frame inference time in microseconds is shown. Excluding the substantial time cost of capturing and retrieving the image data from a separate camera for computation on the CPU, GPU, and VPU, which is shown in red, the CAM5 FPSP is already much faster than the CPU and GPU and reaches almost the same speed as the VPU. Note that these figures include the total time for inference. In other words, both the convolutional part and the fully connected layer. In the case of CAM5, the transfer of binary features from the focal plane to the host is also included. In practice, the data retrieval bottleneck is a major limitation on frame rates achievable on CPU, GPU, and VPU. The FPSP does not face this bottleneck because the image data is processed in place at the pixel level. Taking this time into account shows the clear advantage of realizing most computations directly on the light sensor. The image retrieval latency is simply reduced to 0. On the right, you see the energy consumption per frame. Compared with CPU, GPU, and VPU, FPSP consumes much less power per frame, which makes it an ideal choice for mobile robotic applications. The last application is a visual odometry algorithm on FPSP coined BitVO. Here we implement a pipeline with the distinction that the feature extraction is performed on the CAM5 FPSP. Instead of sending the whole image to a host, here we only send the features. This enables the camera to work at a much higher speed, eliminating the motion blur. This algorithm is the first 6 degrees of freedom visual odometry algorithm which utilizes the FPSP. The entire system operates at 300 frames per second in a natural scene using binary edges and corners extracted by this CAM5. In the next slide, you will see an extensive evaluation of BitVO algorithm, including difficult scenarios such as violently shaking the device 4 to 5 times in a second. To summarize, conventional standard cameras have been used in many robotic applications. They occupy the bandwidth of the system by sending repetitive and unnecessary data. They also suffer from the motion blur. Event cameras transfer only changes in intensity and can operate at very high effective frame rates with no motion blur. Focal plane sensor processor arrays, or FPSPs, are programmable vision chips that can extract and transfer many features such as changes in intensity, computer vision features, feature maps of neural networks, and so on. FPSPs operate at very high frame rates, are very power efficient, and cause no motion blur.